All right, so I believe we are now recording, and I'm going to start off by sharing my screen. So today we're going to look at the first section of chapter 3 and maybe even the second section. Let me just actually pull up a view of the book for a minute. So essentially, okay, so I think I have a search open here, which is not necessary. Right. So, chapter 3 is about applications of deBruijn sequences beyond magic tricks. Although I think there is also some discussion about how they tried to use generalized deBruijn sequences to design a magic trick and they were not successful. Okay, by the way, I just want to confirm that I'm audible because my microphone is not showing any feedback in the Zoom UI. Can somebody just drop a +1 or a yes? Okay, thank you, Sunita. All right. So I think there are a couple of cool applications that are mentioned right off the bat. So again, just for context, in terms of where are we right now? So in the last couple of sessions, we looked at how we could use deBruijn sequences to set up a fairly impressive magic trick using 32 cards and a predetermined sequence and either some memorization or some calculation. And we saw how deBruijn sequences can be generated by taking an Euler tool and an appropriately set up graph. So that's what we've done in the last couple of sessions. And this deBruijn business continues into chapter 3 and 4. So in chapter 3, the focus is, as far as I could tell, there were no new tricks here, but there were some very interesting stories, and there was some discussion about applications of these sequences, and some commentary about different kinds of math and recreation versus research. So I'll try to highlight some of the comments that I found interesting. And then when we go back to chapter 4, I think we have more things to look into, including actual tricks. Okay, so with that set up, let me just start off with the first application that they talk about is this idea of robotic vision. And so here they're saying picture a robot that's trying to go up and down one long corridor. And if the robot wants to know where it is in this corridor, then it would have to essentially keep track of all the movements. Let's say it starts at some origin, and as it's walking, it would have to keep track of increments and decrements based on how many steps it moved to the left or the right. And in some sense, it can track its current position, but it would have to do some calculate, would have to kind of at least keep its current position, and then as it decides, every time it decides to move, it would have to remember to update its current position based on how much it moved and in which direction. So that means that at every movement, not only is it expending compute to actually execute the movement, but it's also executing a little bit of additional compute to update its location data. Right. So if you want to avoid that little bit of extra movement, but we still want to make sure that the robot can always, at any point of time when it wants to know where it is, it should be able to do that, even though it's not explicitly stored its location in memory. It can do that if the floor is colored according to a deBruijn sequence, because then it can just look down at wherever it's standing and it can read off, let's say, just like we did in the card trick, it can read off the 5 bits starting from the position where it's standing all the way up to like basically the next 4 bits. I'm not completely sure how they handle wraparound, so because I'm not sure, let's just assume that it's a circular corridor or something with no beginning or end. And so you can look in either direction, or in particular, wherever you stand, the next 5 bits will always be within your local peripheral vision. Uh, or just like the next 5 bits you can see. That's local information. But because it's a deBruijn sequence, when you read off 5 bits, you also know exactly where you are in the sequence globally. Again, just like in the card trick, you knew where the cut happened if you knew what was the color state of the 5 cards from the top of the cut. So this is kind of interesting that you can use this. You can use this for a robot to figure out where it's standing without having explicitly kept track of its movements as it goes around moving on this corridor. The next point they make is that, well, the more realistic way of modeling robotic movement is along not a corridor or an array, but actually a 2D space. So this I thought would be nicer to do as a interactive. So I put something together and I hope it works. Uh, right. So this should also be live on the website, but I'll link to it right after this session. So actually, let me just check if it's also live on the website, because if it is, then you can also look at it in your own browser. Or yeah, so this works. So let me drop a link in the chat. Uh, so feel free to do this at your end, or you can just look at what's happening on the screen. So essentially, here is a 4 by 4 grid, right? And if you think about a two by two matrix, or a 2 by 2 grid, or a 2 by 2 binary array, the number of states that a 2 by 2 binary array can have is 16, because there are 4 locations and each location is either 0 or 1. So you have 2 raised to 4, and that's 16. And a 4 by 4 array coincidentally has 16 locations, right? And such an array, of 4 by 4 array with 0, 1 entries, is called a 2D deBruijn array with a 2 by 2 window size. If you take a 2 by 2 window and move it around in this array, right? Again, with wraparound, so we'll come back to that in a second. So far I've moved it so that the top left corner of the sliding window has been like in the top 3 by 3 subgrid, right? So I've moved it across all that. And this will generate for you, I think, 9 patterns. You can see the patterns at the bottom, I hope. So scene 11000010, and so on. So you've seen 9 of these patterns, but there's no reason to confine the top left corner to the 3 by 3 subgrid. You can also move on to something to like I can move one step to the right from here. So what's going to happen is that the window will just wrap around. So that gives me, so I can go down this path. That gives me 4 extra patterns. And I suppose the other place I stopped here, so I can also go further down and get so this is like this top left corner being the bottom left thing, and that is spilling over on the top row. So when I hit rock bottom on this array, the bottom half of my 2 by 2 thing is going to manifest on the top. So this is just like when we say, think of your deBruijn thing as a cyclic permutation. It's kind of a similar situation. And I think, yeah, so let's just, I think I have to generate a couple of more. Yeah, so these were on the edge cases. Now I think we have all the 16 patterns. So I guess, let me just make sure. Yeah, so this, I don't know if this particular pattern with the 4 corners looks a bit confusing, as in what is the top left corner that generates this, right? So this is essentially when you get pushed over the edge from this side. So it's when the top right corner of the big grid is the top left. Well, I shouldn't say that's the top left actually, because if that's the top left, let me just restore this. So if this is the top left, then you're actually going to get this. So it's actually when the bottom right corner is the top left corner. So when the bottom right corner is the top left corner of the 2 by 2 subgrid, then notice that the 2 by 2 subgrid, the thing to its right will spill over from the left, and the thing from the bottom will spill over from the top, but it doesn't even have space. So that's going to again wrap around and come back. So when I'm looking at these 4 highlighted entries that you see here, top all the 4 corners, that is going to basically correspond to the idea that you're wrapping around from the bottom right corner. So give me a +1 if this makes sense, the way in which we are like moving around. So actually this may be even nicer to do with like a physical manifestation, in the sense that you can try to keep a small, like imagine drawing a 4 by 4 grid, but then having like tracing paper or something, which is a 2 by 2 grid, and imagine just keeping it and moving it around. That will give you 9 of these patterns, and then you'll have to use your imagination a little bit to do the wraparound. I mean, I guess if you can imagine putting this 4 by 4 grid on a torus-like object or something, then you won't even have to imagine so much, because on the torus, these wraparounds become very natural. So hopefully that sort of makes sense. So by torus, I just mean imagine that this was drawn on a sheet of paper and you rolled it into a cylinder. So that will bring the right column aligned. It'll bring the rightmost column to be next or adjacent to the leftmost column. So now you have a cylinder, and then you can take the cylinder and stretch it around to a donut or a vada shape. Okay. And that will bring the bottom row adjacent to the top row, and then the wraparounds become clearer, I guess. So this particular grid has the property that it generates all the 16 patterns. So just let me know if that was clear or if you have a question. If you go out from any corner with just one of four squares, will you get the same pattern? So here I think the idea is that each one of the base squares, so each one of the squares in the 4 by 4 grid anchors the top left square of a 2 by 2 subgrid, right? So depending on where you are, so for example, if I take the square in the second row and the second column, that is the top left square for this highlighted 2 by 2 subgrid, and that is giving me the all zeros pattern. So every square, each one of those 16 squares in the base grid are responsible for anchoring, in some sense, 4 by a 2 by 2 subgrid, possibly with wraparounds. And our point is that each of these will generate a different pattern for us. Okay, so that is kind of the idea. So here I'm just moving the sliding window. So that, for example, this would be here, the top left square is this square, which is in the third row and the last column. So that would be the square to the bottom is 1, and the square to the right of 0 is 1, and the square to the right of the bottom 1 is a 1. Okay, so uh, yeah, top left square in every position. Yeah. So I think if you play around with the simulation, hopefully it becomes a bit clearer. But try to target every possible square to generate all the 16 patterns, I think. I don't know which one I'm missing here. I'm missing. Yeah, okay. All right. So now I think I have them all. So again, we could ask this question. I'm actually not completely sure. How do you generate? I don't know if it's haven't like I don't know if we can again set up a auxiliary graph where taking an Euler tour gives us some clue about how to generate such a grid. It's not obvious because unlike before, where there was just one direction in which you could walk, now there are. So remember when we did the Euler tour, we said, well, every edge that we take in the tour generates one extra bit of the sequence. And therefore, like when we take a Euler walk, we naturally generate a bit stream. Now, what I'm not sure about is by taking a Euler walk, how can we naturally generate a 2D array? You could say that, okay, maybe we take 16 steps and we just take a 16 length string and then chop it up into 4 length strings and just put them one below the other. But then the thing that is a little unclear is how do you take these, like how do you encode the idea that all these 2 by 2 patterns actually show up somewhere in this particular way, meaning, so for instance, this square here is a combination of the one, two, three, four, five, sixth and seventh bits of the string, and then 9, 10, 11, 12. So 6, 7, 11, 12. So in the Euler circuit, how do we ensure that these things are being captured in some meaningful way? So this is not clear. And I don't think the book talks very much about how these sequences are generated. One thing that I actually wanted to make a simulation out of, but I didn't have a chance, was this idea that they have that you don't have to stop at 2 by 2 and 16, of course. And if you have larger windows, so for example, with a 3 by 3 window, the number of configurations that you can see is 512. Now, I'm not completely sure what is a suitable array size. So I want a grid which has 512 squares. So of course I could do 1 by 512. We could do well, what else does 512 divide nicely? So we could of course do 256 by 512. We could do 8 by 64. We could do a few other options. Uh, yeah, powers of 2, exactly right. So because 512 is 2 written out 9 times, you take whatever combination you want of 9 written as a sum of two things. You can do 9 is 5 plus 4, so 2 to the 5 by 2 to the 4, or 2 by 2 by 2 to the 8, 256, etc. So you could just experiment with all of those combinations. Of course, you could also uh, yeah, I guess you could also say that you'll take a smaller grid. So I don't know what's the square root of 512 is. What, 23 times 23 is too big. It's 529. So 22 by 23 is 512. If you want a square grid, you could do a 22 by 22 grid. It'll have 484 locations. So you could still insist that every square gives you a distinct pattern, but some patterns you may never see because there isn't enough space to pack in everything. So, or you could do a square grid like 23 by 23 and say that you'll allow some patterns to repeat, but that doesn't seem as elegant or as useful because remember, the application is still that local information should convey global information. So, uh, yeah, so this was this cute thing about, some of the things they say in the book. Like you cannot do these large number of configurations by hand, of course. So they say that, well, you might say I need a mathematician, but if you pick a mathematician at random, you're likely to get, I don't do stuff like that as an answer, which I think from whatever little experience I have is actually surprisingly accurate. So, and I think they do explain that this is because most mathematicians like working with continuous objects, which are kind of rounded off and smooth and nice, and this is like usually too discretely for um, for most of the mainstream math folks, but you could instead say that you're looking for a combinatorialist, like the authors of the book. Those are the kinds of people who like to worry about such problems. And I think they do say that at the time of this writing, most of these deBruijn, 2D deBruijn generation questions are open. So one way that you can generalize is go to higher dimensions, but here I think they stick to 2 dimensions, but varying window sizes. So your window doesn't have to necessarily be a square window. You could also do like a 2 by 3 window, or yeah, in general, you could do a S by T window. And there's also no reason to stop at binary. So instead of saying that each entry is a 0 or a 1, you could say each entry is 0, 1, 2, or as they say here, you can think of it in terms of colors, which I think is interesting way of thinking about it. So if I use red, blue, green instead of 0, 1, then I get, even with the 4 by 4 array, instead of getting so each cell previously had two possibilities. So we had well the okay. So if I have a 2 by 2 window, then we said that each cell had two possibilities, so there's 16 possibilities. Now, if each cell has three possibilities, so the number of 2 by 2 subpatterns that you can generate is 81. So you could concretely think about, like, can I come up with a 9 by 9 grid whose entries are all red, blue, or green, such that if I move a 2 by 2 window, I see all the patterns, right? So that's an interesting concrete question. And then they have a similar concrete question: is there a 27 by 27 array where you can get all the 2 by 3 windows? So with the 2 by 3 window, we have six, and like this would be 3 raised to 6, right? So 3 raised to 6 is 729. So that number fits perfectly in a 27 by 27 grid. So you can basically generalize this question given a base grid size, given a window size, and given a number of colors. Can you come up with an array? Can you construct it? How many are there? And are there efficient constructions? All of these are valid questions. And according to the authors, I actually didn't have a chance. I was hoping that I can try to look up what is the current literature on this, because the book, it's been a while. So possibly there are some results about generation of these 2D deBruijn sequences, but I will not be surprised if, maybe some of it is still open. So now they have this nice anecdote about, the patterns don't have to be like nice 2 by 2 square subgrids. The patterns can be anything. So for example, it could be a cross pattern, and this is a trick that I think one of the classes they were teaching, some students came up with this idea for a trick where basically you draw a map, which is, I mean, basically a grid. And let's say again, you have a 4 by 4 grid, and you can give names to every location in the map. And you can have a weather state. You could say, okay, this city is sunny, this city is cold, and so on. And what you can do is have, like, turn your back to the audience, have the audience, somebody in the audience select a location, and tell them, okay, don't tell me anything about your location, but tell me how is the weather in your north neighbor, south neighbor, east neighbor, and west neighbor. So they'll say, this is cold, this is hot, this is cold, this is cold. So you have a pattern, you have this cross pattern. And the idea is just like we did in the other card trick. Hopefully, these 4 bits of information will uniquely nail down the uh, the location where the audience has the location that the audience has picked. So this was the hope, and they said, well, can you come up with a actual array where all of these cross patterns are unique? And they do say that sadly, it turned out that this was not possible, and that they actually managed to prove that it's not possible. So this again, the only thing I did here was to try and turn this into a game, which you can also play from the website. So I don't have a proof for why this is not possible, but the game comes in two versions. So in one version, there is a random coloring of a grid, which has, I think, an equal number of, let's see, so one, four, eight. Uh, so 8 squares are colored one or whatever, they're colored blue, and the remaining 8 squares are white. And the challenge is to find two locations where the cross patterns are the same, because the claim was that there is no there is no arrangement of 0 1 bits on a 4 by 4 array where no matter where you go, you get a distinct value. So there are numbers here. So maybe I'll just pause here for a few seconds to ask if, like, can you give me two locations where, if so basically here, for example, I see this cross pattern around surrounding this location. The bit at the location itself could be different, but what I want is the surrounding four neighbors, north, south, east, west, to have the same cross pattern. So here these don't work. Uh, yeah, so I guess this is just to get a feel for what the claim was. I think this is just a nice thing to play around with. So remember, this is a wraparound. So when I do one here, To its right, I have 2. To its bottom, I have 5. To its north, I have 13. And to its west, I have 4. So that's why this is all white. And was there all white somewhere else? I guess not. This is a all blue. Okay, 6 and 15 are the same. Thank you, Vinod. All right, so 6 and 15. Okay, I would say almost, except I think it's flipped, but you want it to be, I think, exactly the same. Um, let's see if we can find the 15 pattern. Yeah, I was gonna say maybe 4, but it has 3 blue and 1 white. So yeah, this game turned out to be a little more annoying than I thought it would be. Uh, oh, I see. So yeah, I think every time you load the page, I see. So I think if you're playing on your browser, yeah, every time you load the page, you get a random grid. Yeah, good point. Um, okay, these two are the same, 7 and 14. We have, as you can see, uh, the north and the east neighbors are both blue, and the west and the south neighbors are both white. And so that makes some sense. So you can reset this and practice again if you like. The other version of the game challenges you to like pretend that you didn't know this result. So it says, well, can you come up with some, color pattern, which is such that at the moment I'm of course clicking randomly, but which has the property. You don't have to necessarily color 8 squares. You could color fewer than 8 squares if you like. But yeah, it's essentially like once you have proposed something, it's going to find you two locations in what you have proposed. And you can see that they both have the same. So this is just to say proof by example. It's of course a little bit silly, but yeah, if you just want to get some practice with just seeing what these cross patterns look like, these could be two games that you might want to play. Um, on the other hand, yeah, I mean, it would be really nice to come up with a proof for why there is. It feels like it should be some sort of a pigeonholing argument that there isn't. It isn't purely a space thing because clearly, in principle, there's enough space, but I guess things overlap too much, and you can't really, like, no matter what you do, you're going to get stuck somewhere. So yeah, this is a randomly generated grid, and your task is to, find two similar looking states. Okay, I think I should probably reset this. Okay, for some reason, oh, I think that's that because, okay, maybe I should just refresh. Yeah, now this seems to be working. So I think if you move away from one game and start playing the other one, this one is a little buggy. Sorry about that. But by and large, if you refresh, I think this should work. All right. So hopefully the mechanics of the like what we are doing is clear. Like I said, I don't actually have I don't have an argument for why this is impossible, but it's also like I think you could take your favorite like a 2 by 2 polyomino shape. It doesn't have to be the 2 by 2 square. It could, for example, be a L-shaped thing or some other thing. So the cross they've already ruled out. It could be some other shape, and you could ask, well, if that shape was your window, what can you do? And in fact, the next thing that they do, this is, I'm sorry, this is a little messed up. I still wasn't able to completely fix this, so I will share instead what is in the book. Uh, yeah, so here they basically say even on a 1D array, instead of looking at 5 contiguous bits, right? Here is a deBruijn comb, which basically says at a particular location, instead of looking at that location and the next 4 bits, I look at that location, the next bit, then I'll skip the next bit, then I'll skip three, and then I'll look at the next bit. So it's actually an 8 length window from which I'm scratching out some bits and I'm reading four. Okay. And so if I slide this kind of a comb, which makes some locations opaque and some locations transparent, they have this example here of a sequence where you can imagine, I don't know if maybe the font on the screen share is too small. Let me see if I can zoom in a bit. So, yeah, so this is an example of a pattern. If you were to slide this cube, which exposes the first, second, fourth, and eighth bits, and slide this cube with a wraparound, you every time you see a different pattern, right? So I think this is an example of a comb that actually works, length 16. And again, I think they do say that it's open to figure out, like if you were given a general comb, can you come up with a sequence, and how many such sequences are there? So this one, I think they've manually verified that this is actually unique. So unique up to essentially moral isomorphism. So if you flip the zeros and the ones, it'll still work. If you take any cyclic shift, it'll still work. But other than that, there are no other deBruijn sequences that work for this particular comb. And it appears that because they're saying it's done by computation, I think it's a brute force verification. Again, I don't know what are the kind of techniques you would use to say, uh, excuse me, to say that for a given comb, there is no solution, or there's exactly one, or there's more than one. So that's a, excuse me, that's an interesting family of questions. And let me also show you one other real world application that they have, which is up here somewhere. Yeah, excuse me for a second. So this again, this was recent at the time of the book being written. I don't know if modern technology still uses something like this, but I thought it was really cool. So like if you go to Amazon, you'll find these digital smart pens, which like if you were to write with it on special paper that comes with the pen, and you can buy more of that paper or you can print more of that paper. Um, if you write in special paper that comes with a pen, then you can have an app, or the pen itself will be able to record all the strokes that you make. So as you write, you instantly have a digitized version of everything that you've written with that pen. And they claim that one of the ways that this is done is by having some sort of an invisible 2D deBruijn pattern printed on the paper. And so the electronic pen, as it's moving around, it probably has a sensor or a tiny camera. I think probably a sensor makes more sense. So it has a sensor that can pick out that invisible pattern. Yeah, actually, I have no idea what sort of. I mean, I've seen some of these smart pens let you actually print out, the paper that would be compatible with these kinds of pens. So it's possible that it's actually a camera that's able to read some underlying line pattern or dot pattern or something like that. But the basic idea is the same, that the pen's sensor or camera can only see a small neighborhood of where the tip of the pen is. So the idea would be that just that much information is enough for the processor in the pen to infer where it is globally in the entire sheet of paper. So I can see that this works in principle. In practice, maybe some more engineering refinements are required for this to work smoothly. But at the heart of it, I think it sort of makes a lot of sense. So those are like, I think robot movements and pen movements were two concrete applications. And I think they closed the section with this really sweet comment, which is saying that, well, we had a practical use, which was this robot movement or this pen movement, which motivated the definition of 2D deBruijn arrays. And then, because they wanted to invent a magic trick based on this, they invented this idea of a comb or a general pattern, like a cross pattern or whatever. Once you pose these questions, these become research questions to which probably like some answers are still unknown. So the point to make here is that there's a lot of organic back and forth between real world applications, recreational math, and math research, and you kind of go back and forth between all of these in your exploration. So I thought that was a very interesting comment that I found very relatable. So it was nice. I mean, I don't want to. Yeah, I think that's all that I think that covers most of the ideas in this section. Unfortunately, the main concrete claim made here, which is that the cross pattern is not realizable, comes without a proof. And unfortunately, I was not able to come up with a proof, so I just turned it into a game where you, once you get sufficiently frustrated at not being able to construct the pattern, maybe you'll be convinced that such a pattern doesn't exist. So it'll be nice to see if we can get a proof as well. Apart from brute forcing, brute force should be feasible because there's probably, I think, about 65,000 different patterns to check. So that should be doable by computer, but it would be nice if there was a combinatorial proof. I think tomorrow we were supposed to discuss code, the crypto applications, but I think this is something that um, yeah, I think this is something that I'll probably take the liberty of skipping, or I'll just like quickly tell you what they're trying to do here. So essentially, they're saying that you encode messages by taking, like, let's say this is your original plain text, which is the message you want to convey. And then you have a corrupting string, which is another bit string, which is there with both the sender and the receiver. And the message is obtained by XORing the plain text with the corrupting string. And if you are the receiver and you have the corrupting string and you receive this message, because XOR is basically like if you do XOR again, it will undo the first XOR and the original base message will be received, will be revealed. And the point they're making here is that, in the old days, and they actually have a nice, I actually haven't read this, but I think they have a nice suggestion. One of the most exciting true spy books we have read is Leo Mark's Between Silk and Cyanide, A Codemaker's War, 1941 to 1945. So this is something that I bookmarked for myself to go and look up, and you might also find it interesting. But yeah, so their point here is that the most secure kind of corrupting, because the thing is, if you have the corrupting message and you have the encoded message, you can retrieve the original plain text. So of course, for any eavesdropper or for anyone else, it's crucial that they don't have the corrupting message. So you could do one-time pads, which was, I think, a traditional method that both the sender and the receiver, they have a common pad, which, every day you can tear off a piece of paper that has the corrupting string. So for that day, when you're transmitting a message or for that hour, you use, I mean, so you're globally in sync that or the other thing that they do is they'll say that on the daily newspaper and you agree which newspaper. So let's say the Hindu front page, first article, first sentence, somehow that gives you you take that sentence, convert it to binary, and that gives you the corrupting string. So you and I, if we are trying to communicate, we have this silent agreement, so we know what the corrupting string is. And somebody who's eavesdropping on the channel, for them, they hopefully will be clueless about what the corrupting string is. But I think all of these methods have their limitations. So I think the reason they connect this with deBruijn is they basically say that you can use deBruijn sequences. So this is actually related to something that Sunita said yesterday. For deBruijn sequences of order 3, they point out that you can start with 001 and add the first and the last bit to get the next bit, I think. So appending the sum of the first and the last symbol and then getting rid of the first symbol. So basically 001, you add 0 and 1, you get 1. You drop the first symbol, so you get 011. Once again, 0 plus 1 is a 1. Drop the 0, you get 111, and so on. So this process gives you the entire deBruijn sequence of 8 strings. And they're saying that for a message string, like basically which string is used as the corrupting string, this sequence of these deBruijn strings gives you a way of agreeing on a corruption mechanism. And according to them, the data encryption standard, DES, actually uses, under the hood, they use these deBruijn cycles to do this encoding, decoding thing. And so therefore, there is basically some form of crypto that I think, yeah. So here they do have an example, which was actually, to be honest, not entirely clear to me. I think they say that you can get a really long sequence by adding, yeah, basically this is I think what we saw for window of length 5. So they say start with a bunch of zeros followed by a 1. Add modulo to the last entry plus the entries 2 behind and the entries 5 back. So I think you take 3 bits to get the next one and so on. And the resulting sequence will continue without cycling for another 2 raised to 20 terms. So this is the part that I didn't verify. I don't know if it's 2 raised to 20 because this initial string has length 20 or something like this. Yeah, so this is something that wasn't entirely sure what's going on, but I think the next thing that this is sort of clarifies that you can use, so starting with 001 and following this formula that, okay, you take or start in general with some bit string and get the next bit by adding some combination of bits in the current string and drop the first bit to generate the next k-length bit string. So this gives you so basically, this is a replacement for a one-time pad. So you now have a very large supply of, like, so if you want to know on the ith day what should be the corrupting string, if you know which deBruijn sequence or which combination of bit patterns you're adding in the starting string, then basically the entire corrupting string mechanism is determined by that. This is at least what I got out of what they're trying to do here. And their point is that this is something that actually made its way to hardware, and apparently the authors were also involved in coming up with some sort of a mechanism for like a chip to protect special event TV shows. They came up with a scheme involving deBruijn sequences, and in general, it's useful in crypto style applications. So basically, this section is predominantly story with some ideas about how uh, like the mechanism for generating deBruijn bit patterns can actually be a good replacement for a one-time pad. I think that is the main technical point being made here, and there's some nice anecdotes and nice pointers to spy books and anecdotes about crypto applications that use math. So that's what this section is about. So when we pick this up tomorrow, I think we will look at the other half of this chapter. So here they're talking a little bit about DNA strings and some connections again with this deBruijn style of operation. And again, some very fun stories about problems that came up in a math meeting where some of these issues were being discussed. So again, this is a little more story-like as opposed to, I mean, I think there's some very interesting math claims that were made here, but at least so far I haven't had a chance to actually dig into like further references or look up any proofs. Maybe by tomorrow, if I have something, we will discuss it. Otherwise, we'll kind of roll through the rest of this chapter, go over. I think here there is some nice concrete ideas. So the bit about like the connection with DNA sequences and our kind of sequences. So that's what we will do tomorrow. And we might actually end up being like slightly ahead of schedule if we manage to finish chapter 4 tomorrow. Then day after we can start off. Sorry, if we finish chapter 3 tomorrow, then day after we'll start off with chapter 4. It's the current plan, and the playable. So the deBruijn comb interactive is not complete yet, but once hopefully I can get it to work. But the games with the crosses and the 2x2 window, those two are available from the notes on the website. So I'll also post a link in the group. Um, hopefully it's functional and not too buggy. Let me know if you encounter any issues. But that's about all I have for today. So questions or comments welcome. But if you don't have any, then we can wrap it up here and pick this up again tomorrow. I can't be sure if anybody is typing anything out. Thanks, Ravi. Also, like I said, just feel free to unmute if you had anything. But if you don't have anything right now, but something occurs to you later, please post it in the group. I'll watch out for your messages. Meanwhile, I think maybe this is a good time to wrap up. Let's catch up tomorrow, talk about DNA and some other fun stories from our friends Graham and Diaconus. So we will stop here. Good night for now. Okay. All right. Sorry. So Sunita has a comment. Looks like a 16 length deBruijn sequence can be used to create a 4 by 4 grid. That's you mean by chopping it up and aligning. So 16 length deBruijn sequence treated as a one-dimensional sequence, and then you can chop it up to make it a 4 by 4 grid. Okay, that is very interesting. Let me well, I mean that's something that we can physically validate and perhaps even prove. And then I don't know if then we can, then maybe there is some hope for using this Euler-Tour mechanism for generating 2D deBruijn sequences. So that would be very interesting if true. Um, and the other thing is, I don't know how, like, I don't know if this particular 4 by 4 deBruijn thing can be used to make a magic trick. They tried to do it with this cross thing and it didn't work because the pattern doesn't exist. But maybe the 2 by 2 thing can be used in some way to set it up. Okay, so Akash is saying for 2D sequences, you can bank on integer overflows and pad sequences. But thinking about spaces to be tori or circles is best. Yeah, at least for understanding the wrapping, I think it makes sense. I'll have to pass the rest of your comment, Aramse, but yeah, to understand wraparounds, it's probably very convenient to think of the grid as being embedded on a torus. Um, Okay, Sunita, thanks for verifying that. Well, if you don't mind, I'll just post your comment to the group. So in case anyone else is also interested in picking up this thread of thought, they can. Um, I I think I will also like I'll cross-validate this. But just to be clear, yeah, thanks very much. Just to be clear, you're not claiming that every 16-bit deBruijn sequence can be turned into a 4 by 4, but you're claiming that there are, and in particular this one, will also work as a 2D sequence. Correct. Okay, great. So I'll try to either add this point to the notes or put it up in the group, and we can try to dig a bit deeper into this line of thought, maybe especially when we meet tomorrow, because I think the discussion of the material in the chapter should be brief. So if we all have a few minutes to spare, then we can maybe try to dig a little deeper into the question of generation of 2D deBruijn sequences, because the information on what can actually be done is a little sparse in the chapter. So if we can come up with any ideas, or if anybody comes up with any references, that would also be nice. I'll also try to do a little bit of homework. I think I spent most of my time just reading the chapter and didn't have a chance to look beyond, but I'll try to do that a little bit too ahead of tomorrow's session. Okay, everyone. Thank you so much for joining in. Lovely catching up again. And hopefully see you tomorrow evening then. All right. Bye bye. Good night.